So last time we were talking about angular momentum, and we're going to continue to talk about angular momentum and how it interacts with torque. So we're going to talk about a very specific phenomenon today. We're going to talk about a phenomenon called gyroscopic precession. So first, I want to ask you guys if you've ever been nerd sniped before. I don't know how common of an experience this is, but when I was writing up my notes this morning, or rather fixing my notes this morning, I came upon a really interesting problem in the thing that we're going to talk about today. And then I wasted about an hour and a half trying to solve it. Turns out it's a hard problem. So that's a bummer. But you'll see. You'll see how this gets interesting. It really does, at least from a physics perspective. And this has to do with gyroscopic precession. So I want you guys to think back to like second week of lecture or something like that. When we first started or before we even started talking about circular motion, just an object moving in a circle, we did this thing where we decomposed the acceleration vector that an object has. We decomposed its acceleration vector into an acceleration that's in the direction of motion, i.e. speeding up or slowing down, and an acceleration that's perpendicular to the direction of motion, turning. So we can do the same thing in terms of momentum. So in terms of momentum, we could talk about the change in momentum as either its magnitude or its direction. And remember that the change in momentum, the time rate of change of momentum, is the net force. So in particular, we could write the net force as the change in the magnitude of the momentum times the unit vector in the direction of the momentum plus the magnitude of the momentum times the rate of change of the unit vector of the momentum. This is just the product rule, remember. And so this is the same thing that we did before. It's just before we had v, we had dv dt. But here the mass isn't changing, so this is just a momentum way of viewing the exact same thing. So this vector here, the time derivative of the unit vector p, indicates that the direction of motion is changing, whereas dp dt without a unit vector, this characterizes the changing magnitude of the momentum, speeding up, slowing down, that kind of thing. So, and remember that these two vectors were perpendicular to each other. And we found that by doing some magic algebra. And again, I'm framing this in terms of momentum, but we did this in terms of acceleration. But what we did in order to understand circular motion is we analyzed the perpendicular aspect of the motion, that is p dp dt, dp hat dt. We analyzed what happens when that one's not zero and this one is zero, and that led to circular motion. In particular, we got that this is equal to the mass times the acceleration in the perpendicular direction, which gives us circular motion. The object's speed is never changing, but the direction constantly is. And now that we've actually discussed angular momentum, we can do the exact same thing relating angular momentum to torque. In particular, we can write that the net torque on an object, which is equal to the time derivative of the angular momentum, that's equal to the time derivative of the magnitude of the angular momentum plus the time derivative of the unit vector of the direction of the angular momentum. And so in particular, if L, the magnitude, is held constant, but the direction is changing, the direction meaning the unit vector, we might similarly expect some sort of circular motion, just a different kind. Just in the exact same way that we found circular motion in the regular momentum and force case. So in this scenario, we have that the net torque is equal to L times dl hat dt. And that's because the magnitude isn't changing, so dl dt is 0. So the question is how do we build a system? How do we build a system like this? Like what would be a good example? So to build a system that and the reason why we want to do that, by the way, is because we want to investigate what happens when you have the same sort of phenomenon occurring for rotational motion. To build such a system, we need, or rather, we notice that dl hat dt as a vector is perpendicular to the momentum vector. So we need a system where the torque, because the torque is proportional to dl dt, sorry, dl hat dt, where the torque is perpendicular to the angular momentum. And that would be like saying, in the case of regular circular motion, like an object, like a rock tied to a string going around in a circle, the force, which is the tension force on the rock, which is pulling it towards the center, is perpendicular to the momentum vector, which is going along the circle, right? Those two are perpendicular. We need the same thing here. We need that the torque is perpendicular to the angular momentum. So we can just try to come up with an example. There's a standard one that we're going to go over, and it involves a gyroscope. So there's actually a neat video, but I'm going to put off watching it. Actually, no, let's try this. I'm just going to try to skip along to the, I don't want to give away the explanation, but I think it's here. I'm going to share a new screen. It's Veritasium, excellent YouTube guy. Hopefully you guys can hear this.
Point there. So if I let go, well, it does exactly.
Sorry, I'm still skipping around. Oh boy, my tablet can't handle it. Yeah, no, we are very much dropping FPS. I just want to show you an example of it happening. I would normally do this in lecture, but I can't. Okay, here we go. He's doing it. Okay. This is the kind of thing that we expect to happen.
It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque.
So this is the kind of thing that we're going to try to understand. That it's a standard physics demo, and I would suggest that you watch the whole thing. It's a great explanation. But for now, and it's linked in the lecture. It's linked in the lecture notes. But for now, that we're going to do our own analysis of that. Hopefully the frames aren't dropping now. Yeah, sorry. It is really cool though, and you know I would have loved to have done this in person. We will talk about biking as well. Right. So the picture here is. So we have so the example really is gyroscopic precession. That's really what we're talking about. So the picture here is you have some pivot maybe. You have a rod or an axle attached to a wheel. Coming out, say, the other side, just like a bike wheel or whatever. The wheel is spinning maybe this way with some angular speed omega. And there's a few forces at play. So first of all, there's going to be a force on the center of mass of the wheel due to gravity. It's a force straight down. By the way, I'm going to extend this out just so then it's a little bit easier to see. And I'll draw this so that it's more obvious. So imagine that this is just like resting on the ground or something, right? The wheel's not touching the ground, the thing it's resting on is. There's a normal force pushing up the pivot, say here. But in principle, like assuming that the wheel is, you know, attached to the pivot point, that's really all the forces that are present. And you might intuitively think, well, okay, the wheel's just going to spin and it's just going to fall down, right? But that's not what happens, as we just saw. It's actually kind of amazing what happens. So let's start analyzing this from a rotational perspective. So from the right-hand rule, and by the way, this is supposed to be like rotating, like this side is supposed to be further outside or like closer to you, and this side's supposed to be further from you, just so then we can get the perspective right. So from the right-hand rule, we can automatically figure out what the direction of the angular momentum is about the central axis here of the wheel, right? It should be pointing to the right. So hands rotating in the direction of the wheel, thumb points in the direction of the angular momentum. So we have that the angular momentum points to the right. Now, we don't necessarily want to find the torque about the center of mass because that would be confusing, just because there's a normal force over here. It turns out that the normal force is going to be the exact, or the torque would be the exact same anyway. But let's imagine the torque from this pivot point over on the left here. We're going to try to find the torque there. Well, so we have to use the right-hand rule. We do R. So the normal force doesn't contribute to the torque because it's located at the place where the pivot point is. So the net torque is going to be R. The vector R points from the pivot to where the force is applied. R cross F, which is down. So in this case, the torque, I'm just moving my thumb so you can see it, the torque points into the screen, notated this way. I think I've used this notation before. This is like the backside of an arrow with feathers. L is angular momentum. This is like the backside of an arrow with feathers because the arrow is pointing into the screen. So you can only see the feathers, you can't see the tip. If it was pointing out of the screen, it would look like this. But anyway, so the torque is pointing into the screen. So we can establish that the torque is perpendicular then to the angular momentum. The angular momentum is to the right, and the torque is into the screen. They're perpendicular, they're at right angles. So this would be an example of the case that we mentioned above. So in particular, because the net torque is perpendicular to the angular momentum, that is, we know that this is perpendicular to, or that the net torque, y is r cross f, is pointing from the right-hand rule. We know that the net torque is perpendicular to the angular momentum, which means that this first term has to be 0. Let me write that out. R, stick my hand in the direction of R, curl my fingers in the direction of F. So my thumb points into the screen. That's the right-hand rule to get us the torque. So because the torque is perpendicular to L, and the torque is equal to dl dt L hat plus L dl hat dt, we must have that this term is 0, right? Because this part is not perpendicular to L. So if it was, then it would ruin this fact that the torque is perpendicular to L. So this implies automatically that dl dt is 0, or equivalently that the magnitude of L is constant. And only the direction changes. So this is to say that the angular momentum vector is going to change directions, but the magnitude of the angular momentum will not change. This is just like in the case of rotational motion, an object going around in a circle tied to like a string. The speed isn't going to change, but the vector, but the velocity vector will change. It'll change directions, but the magnitude, its speed, is never changing. It's the exact same thing happening here. So what happens then? What actually happens to the motion? So we're going to view this from above and try to understand it because it'll be a little bit easier to picture. So we know from the impulse momentum theorem for rotation that the change in angular momentum is the torque times a duration. So just imagine a really short duration just so we can get an idea as to how L changes. We know what direction torque points into the screen. We know what direction L points, say the initial L points to the right. So we can just compute what direction the new L points after a little bit of time by just using this formula. So this implies that LF, say, this is after a time delta t has elapsed, is equal to Li plus delta L. Delta L points into the screen. We know that because that's the same direction as the torque. Li points to the right. So that means that LF points to the right and into the screen. So I'm going to draw this from above just so you can get an idea as to what this looks like. So we have our, this is viewed from above, by the way, not from below, because that can be awfully confusing. So we have our pivot point. We have our axis, which I'm simplifying to just be a line. Oops, I don't know how that happened. And so from this perspective, the angular momentum is to the left. Let me draw this better. Sorry, to the right, and the torque is upward. Right, this is from above. So at the next instant in time, say LF, if this is LI, by the way, or if this is the initial time, the next instant in time would look something like this. So we know that the angular momentum has to point up and to the right, because that up in this case means into the screen, because we're viewing it from above, and to the right still means to the right. So the wheel has to have rotated a little bit, and the only way that it can stay attached to our pivot point is if it goes around. It can't just rotate without moving because it's attached to the pivot point, rigidly attached. And so viewed from above, this thing is rotating counterclockwise. Or maybe I should say revolving. And then this whole thing is going to continue, because once the wheel has rotated a little bit, now the direction that the torque points also rotates with it, because the vector r has changed. The vector r has gone from being this vector to being this vector. And so now when you take that cross product, you'll get another torque that's again perpendicular to the into the screen, or perpendicular to the down direction of gravity, and perpendicular to this vector r. And so that has to be pointing again along the wheel. And so then it'll just repeat, and it'll just go around in a circle forever. So this is all to say this thing will just spin in circles, and that's precisely what we saw in the video. This phenomenon where you have a spinning thing revolving in a bigger circle, that's called gyroscopic precession. One way to know why it's called that.
Sorry, Professor. Could you explain how you got the direction again
For what?
for this precession?
Well, so all I did was I considered for a moment what the final direction, if you let that torque act for a little bit, this initial torque that we see here, if you let it act for a little bit, how will that influence the angular momentum, right? We know from the impulse momentum theorem that the torque points in the same direction as the change in the angular momentum. And so what we see is that the angular momentum has to be, the angular momentum after a little bit is in the same direction as the original angular momentum, plus a little bit in the new direction, in the direction of the torque. And so you have to take a vector, say this is Li, and then you add to it a little bit of delta L, which is equal to the torque times delta T. And so your resulting vector rotates a little bit. And so you do that over and over again, and you get that your LF rotates around. And that's what that's what's happening. That's how we get this gyroscopic precession in this direction. Now, to answer Jackson's question, the reason it doesn't rotate down to be parallel with the ground because angular momentum is conserved, at least in a sense. It's not conserved in the sense of it doesn't change, because it is changing, but we know how the angular momentum changes. And if the wheel just rotated downwards, its angular momentum would have to be going from the right to going downward, or from the right to going downward. And that would mean that there has to be a torque that makes it do that. Angular momentum can't just change on its own. You need a torque to do so, but there isn't a torque that does that. So it just can't happen. Like the only reason why you might expect it to rotate down is because you're not considering, does gravity not apply? Gravity does apply. Gravity is what's causing the thing to rotate. Notice, by the way, that the net force on the object is 0, right? The net force is 0 because there's a normal force keeping it up on one side and a gravitational force pulling it down on the other side. What you're thinking about is what the gravitational torque would do, because you want it to swing down this way. But we have to just be more careful. We have to actually analyze, what does that torque actually do to the angular momentum? And it turns out it doesn't make the angular momentum just go down. It makes the angular momentum go around. If, on the other hand, the object was not spinning, then the torque would give it an angular acceleration downward, because the angular momentum would go from 0 to pointing into the screen. And so that means that the rotation would be this way. But when the angular momentum is already this way, and then you're just making it go more and more into the screen, all you're doing is rotating it. You're not actually just rotating the whole object down. It's a weird phenomenon. That's why it's really cool, and that's how you end up getting nerd sniped. Yeah, it's very strange. So we can actually think about this phenomenon occurring in real life too, and maybe this will help build up your intuition, like not just in some arbitrary example, because this happens for bicycles too. So think about what you know about bicycles. In order to turn, the rider has to lean, right? That's how you turn on a bike. That's why you can drive. That's why you can ride a bike and turn without actually holding the handlebars. And so let's draw a picture and do some torque analysis, and angular torque and angular momentum analysis. It's a thing that we should do. So I'm going to do my best to draw a picture. Again, sorry, it won't be perfect. So here's the wheel of a turning bicyclist. So they're turning slightly because they want to turn left, right? Assume the person's going into the screen. They want to turn to the left, so they lean a little bit left. That's how you ride a bicycle. And so we're going to assume that the top is rotating into the page, and the just so then the picture makes sense. So this is what I mean when I say the bicyclist is riding forward. So here's the ground. I'm actually not going to draw the ground, but the ground is going to touch at this point. So that's where the normal force is going to contact, and in fact, that's also where we'll see friction. So let's talk about the forces that are involved. So we have a gravitational force downwards. I'm going to draw this in a different color. We have a gravitational force downwards. We have a few other forces too. We have a normal force pointing up from the ground, and then we have a friction force that's pushing it to the right. By the way, how do we know that the friction force points to the right? Well, if the friction force wasn't there, then the wheel would just slide out, right? So the friction force has to be the thing that's keeping it from sliding out. So that's why the friction force points to the right. Okay, now the wheel is also spinning this way. The top is rotating, or from your perspective, it's spinning this way. So the angular momentum, we can figure that out. The angular momentum about the center of mass of the wheel points that direction. Just using the right-hand rule, it's rotating this way. So my thumb points in the direction of the angular momentum, and because it's tilted, it points down a little bit. So hopefully you guys can see why that's the case. So let's actually do some analysis using this bottom point as the pivot point, just to start thinking about torque. So in order for the person to actually rotate, in order for the person to actually turn, and for this to be relevant at all, we need to think about how the torque is related to the angular momentum, the torque on the system. So let's compute. Or let's just figure out directions. So the torque due to the gravitational force, well, stick your hand in the direction of the r vector, so it points up from this is going to be hard for me. Hand points up, and maybe slightly to the right, slightly to the left, whatever. it's this vector here. Oh, instead of just drawing it, or instead of doing it with my hand, it's this vector, right? That's the r vector. So r, and then I curl my fingers in the direction of f, which is basically straight down. But the point is it's a little bit to the left of it. It's not the other direction, right? So it's basically straight down. And so my thumb points out of the screen. So in this case, the torque due to gravity is out of the screen. Now we can look at the torque due to the normal force, but that's just 0 because the normal force is at the pivot point. And similarly, the torque due to the frictional force is also 0. So that says that the net torque is in the same direction as the gravitational torque, and it's out of the screen. So that's what that means, by the way. That's like looking at the tip of an arrow because the arrow is coming towards you. So how does this tell us what direction the counterclockwise, or how does this tell us what direction L is going to move? So again, L is perpendicular to the net torque. So we know that L is going to undergo circular motion. Its direction is going to change, but its magnitude won't because they're perpendicular to each other. So viewed from above, we can actually think about this. Viewed from above, angular momentum is initially, say, this direction and torque is this direction. So then at a split second later, the angular momentum will be slightly down that way. And then a split second later, it'll be that way, and then that way, and so on. So if this was the wheel, and then the wheel rotated a bit, so what we're seeing is that the wheel rotates counterclockwise from above, just from this analysis of how the torque is going to influence the angular momentum. The angular momentum vector rotates counterclockwise viewed from above. But there are other things that are happening here, right? We also know the wheel is rolling forward, right? Like the person is riding a bicycle, they're moving forward. And also, look at the forces at play here. There's only one force in the horizontal direction. That's the frictional force. So that means that the object is also accelerating to the left. So the wheel is accelerating to the left. So let's put this all together and view it from above, just to get this picture down. So
Sorry, why is the wheel accelerating to the left?
Because there's only one horizontal force on the wheel, and it's the frictional force, and it's pointing to the left. Just has to be right. So viewed from above, we have our wheel. So like this is the bottom of the wheel, is how I'm trying to draw this. And then the other side's the top. So the wheel, okay, let's do this a little bit better. So the wheel is moving forward with some speed, with some velocity vector v. We know that there's a torque relative to the bottom of the wheel, which points, in this case, it would point, we knew that it points out of the screen. So if you're viewing it from above, that would be pointing down. So here's our torque. We also know that there's a frictional force this way, F sub s. That's pointing in. It's this force here. And then we know what direction the angular momentum force is. The angular momentum, sorry, not the angular momentum force. The angular momentum points to the left. Okay, so that's a lot of things to label here, but those are the important relevant things. And so at a fraction of a step later, we have to account for all of the things we just said. The wheel should rotate, it should move forward, and it should accelerate to the left. So what does that look like? That would look something like this. And unfortunately, I can only do 45-degree increments, but it would look like this. We can tell that it accelerated left because the center of mass, which was here, moved leftward, right? The center of mass went from here to here, it went left. It also rolled forward because the center of mass moved forward, right? And the wheel turned. But this is precisely what it looks like when you turn on a bicycle, right? You don't just suddenly turn. Your wheels rotate, like they rotate automatically. You don't turn the handlebars, your wheels just do the rotation for you. And you move forward and you curve. You accelerate to the left. You undergo circular motion. like you would expect if you had acceleration to the left and your velocity was forward. So this is like a combined circular motion of an object and gyroscopic precession. The circular motion is telling us what direction the center of mass moves. The gyroscopic precession accounts for the fact that the wheels have to turn as well. What you're not going to end up with is you're not going to end up with just the bike being forward and to the left, but in the same orientation, because the whole thing rotates, right? So this picture corresponds to what we just determined from the forces and the torques. Now, unfortunately, this is where I got nerd sniped. And I'll explain to you why I got nerd sniped, because it gets more complicated than this. So there's something else happening here. Remember, I kind of pulled a fast one on you, because I computed the angular momentum, or I computed the angular momentum relative to the center of the wheel, right? But I computed the torque about a point that wasn't the center of the wheel. So remember that there's a way to relate the angular momentum about the center of mass of an object relative to some other place. In particular, this wheel is both rotating and moving. So as a quick reminder, a rotating and moving object relative to some reference point has a total angular momentum relative to that reference point equal to the angular momentum about the center of mass plus the angular momentum of the center of mass relative to the reference point. Sorry, all these subscripts are long. But the point is imagining an object that's spinning and then you also throw it. Relative to some reference point, the motion of the object itself will have some angular momentum, and then you can add that to the angular momentum of the rotation itself to get the total angular momentum. And so if we wanted to actually compare, if we wanted to actually figure out how this torque affects the angular momentum, we have to talk about the angular momentum using the same reference point that the torque was computed about. So we would need to find the angular momentum relative to that pivot point. But that's kind of confusing. It's more confusing anyway. So I kind of shoved that under the rug. But in principle, we could do that. So let's figure out, so we already know what the angular momentum is about the center of mass. That's the one that's pointing down and to the left. So what about the angular momentum of the center of mass's motion? Well, let's go back up to this picture. So we know that, so the vector r points from the pivot to the center of mass. Remember this is r cross PCM, or it's rather RCM cross PCM. So r is the vector from the pivot to the center of mass, and PCM is the momentum of the center of mass. So the vector r points to the center of mass, and then we cross it with the vector, or with the momentum vector of the center of mass. Now we know that the wheel is rolling forward. So we do r, which points up and to the left slightly, cross p, which points forward. So that would give us, I don't know if you can see this, that, and my thumb's not bending right, but it would give us momentum in the same direction. It turns out that the momentum vector that we end up with, this one, points in the same direction as the angular momentum of the wheel spinning about its center of mass. This doesn't generally have to be the case, but because this is a wheel spinning and moving forward, it is the case in this situation. So the end result of all of that is to say that the total angular momentum, which is what we really should have been considering to begin with, which is equal to, is, how do I want to write this? Basically, it's in the same direction as the momentum, angular momentum about the center of mass. It's just more. How do I want to write this? Yeah, let's just say the total angular momentum also points in the same direction as LCM, which we've already established is down to the left. And so when the torque affects the angular momentum, what it's really affecting is the angular momentum relative to that reference point. So it doesn't just affect this angular momentum, it affects both the angular momentum relative to the center of mass, also points in this, yeah, fair enough. Also points, sorry, talking while writing, if you say something different from what you're writing, it can get very confusing. So this is just to say that the torque affects both the angular momentum relative to the center of mass and the angular momentum of the center of mass relative to the reference point in the same way, because they're both pointing in the same direction. So the torque affects them both in the same way, because all you're doing really is you're just making the total angular momentum just bigger, and the fraction that each part gets is the same. And I can be more explicit about that if I need to, but I don't know if I need to, because this is kind of a fine point. And so this is just to say, not only does the wheel rotate, because really, if it was just the angular momentum about the center of mass of the wheel that's rotating, then it would just be the wheel that's rotating. But it's not just the wheel that's rotating. It's the whole center of mass that's doing this rotational motion, which means the person and the rest of the bicycle also move with it for the exact same reason. Because if this angular momentum relative to the reference point changes direction, that means, and this vector r, that vector r isn't changing direction. So if that vector r isn't changing direction, then the velocity vector has to change direction. So this accounts for the fact that the person ends up changing the direction that they're traveling, because the velocity of the center of mass must change direction in order to account for that change in angular momentum. I know that this is super confusing, and this can get very complicated, but this was but I wanted to make sure that I wasn't lying to you, is the bottom line. The homework will probably focus on this, but I'll try to step you through it. Don't worry. Okay, so this is just to say, this is how bicycles work. This is why you lean on a bicycle, because when you lean, both the wheels that are actually touching the ground are going to rotate. So if they were like this as you're traveling along, they rotate, right? They go from here to here. But also your direction changes direction, or your velocity changes direction, because the angular momentum associated with just the velocity of you moving forward also has to change direction because of the torque that's acting on you, because of this torque, wherever it went, here. Putting that together with the fact that you were already moving forward and that there is a net force to you on the left means that at the same time as your velocity changes direction, you're also moving forward and tracing out a circle. Hence, this is why you can go in a circle on a bike, because if you just lean, you'll just go in a circle. Your wheels will turn, your velocity vector will turn, the friction will cause the force that makes you turn, you'll move forward, it all works out beautifully. Point is that it all checks out. So let's put aside the bicycle, which is a more complicated case. Let's go back and see if we can analyze the simpler case like we did at first. You just have the wheel on a pivot point rotating, and let's see what happens. So let's go back. Let me just grab this picture again. By the way, this is just to say that this whole precession thing happens in the real world all the time, and you don't think it's nearly as spooky when you see it happen on a bike. It's just this particular contrived example seems scary because it looks like something's defying gravity. So back to this case, let's actually do some quick analysis. So let's first note that the torque, the magnitude of the torque, which we established was just was just due to gravitational force. It's just the distance. It's just the distance from the pivot point to the central axis of the wheel times the gravitational force. So this would just be R times M times G. That's just the magnitude. And so this is constant. Like the torque, the magnitude of the torque is constant, which tells us that L, well, remember what torque is. Scrolling back up again. Where did I write out that formula? Here. this is what torque is. So if the torque is constant in magnitude, and we know that that term is 0, which we do, as we've already established, that means that L, the magnitude, times the magnitude of the time derivative of the direction vector, that's also constant. Basically, this is the torque because the other term is 0. And because we know that the magnitude of the angular momentum is constant, i.e. its derivative is 0, we have that the rate at which the angular momentum direction changes is fixed. This is a constant. So this is all just to say the torque is constant, so L times dl hat dt is constant. L is already a constant because the magnitude isn't changing, period. And so that means that this term is constant, which just says that the rate at which it rotates is fixed. It doesn't start off rotating fast and then slow down. It just rotates at a fixed constant rate. So the precession occurs at a constant rate. So it might make sense to ask how fast. So we can actually justify this or answer that question fairly easily. And we're going to do it by analogizing with regular circular motion. So for regular circular motion, we have, a rock tied to a string, some distance r away, traces out a circle, and at a later time, maybe it's over here. So we want to answer the question, what is the angular rate of revolution? This is the rate at which it makes one full circle. So, and we're using rate of revolution rather than like angular velocity because we don't want to confuse that with the actual angular speed of the wheel spinning. And we're going to give it a different name just so it's not confused. We're going to use the Greek capital equivalent of omega. Again, so we don't confuse variables. So in this case, the rate at which it goes around is precisely just v equals r omega, right? In this circular motion case. This is in radians per second, right? R is just the distance, and so this is just basically, it goes out 2 pi r units of distance for every one time it goes around. And it goes around at however many radians per second. And so we can actually figure out this omega from doing just a little bit of analysis. So let's look at this first step. Here, the rock is moving up and to the left, right? And the force is pulling it down and to the left. And they're perpendicular, as we would expect. And so we can actually just use centripetal acceleration to analyze the system. So the force, this is circular motion, should be equal to the centripetal, or the mass times the centripetal acceleration, right? That's just true. And we know what direction the centripetal acceleration is in. It's towards the center of the circle. This should be a vector equation, but I'm simplifying it because the force and the centripetal acceleration are in the same direction. We know a formula for the centripetal acceleration. It's v squared over r. So we can write this as mv times v over r. But mv is the momentum, and v over r is omega from this equation here. That's just the definition of omega, which tells us that the angular rate of revolution is just the force divided by the momentum, which is a really nice and clean answer. And you could go and test this, and you'd find that whatever the tension force is pulling the rock back, you divide it by the mass times the velocity, and you get the rate, however many radians per second it goes around. So we can do the exact same thing for gyroscopic precession. We just argue by analogy. So in this case, we have, a wheel. That's a terrible wheel. Going around a circle. It's attached to a central post. Traces out a circle at some rate capital omega. Again, we'll use r for that distance, and then at a later time, it'll be somewhere else, right? So let's analyze the system again. So we have our wheel. And in this case, we might have L points that way. So here you want to visualize that it's spinning this way as it goes around. So initially it's spinning this way, so L points that way. And we would find that the torque is that way. This is the same picture, by the way, that we had above. It's literally just this picture. So I'm just using this example, right? L points up and to the right, torque points up and to the left. And so here, we again have that the torque is perpendicular to L. So we should be able to use the same sort of analysis that we used up there. In particular, we can just write the answer. So by analogy, because we literally can just swap variables, the rate of angular revolution should be equal to torque divided by angular momentum. And so we can just write out what that is. So let's say that the wheel has radius capital R. So the torque, we've already established what the torque is. The torque is just mg times r, right? We did that up here. We did that somewhere. Where did we do that? Oh, it was nearby. Yeah, rmg. The torque is just rmg. So torque is rmg, and we know what L is. If we assume this is like a thin wheel and so on, we can find what I is, because L is just I omega, right? And so this would be little m, sorry. M times capital R squared, because that's the radius of the wheel, times omega, which is the rate at which the wheel is spinning around on itself. And so we would end up with an angular rate of revolution of rmg divided by mr squared omega, which is just rg over r squared omega. So this is just a relatively nice, neat formula that tells you how fast this gyroscope will spin around. So if you actually got out your calculator and calculated this for the Veritasium video, I bet you the number that you would compute, maybe I'll make that homework actually, just make you actually do that and verify it. That'd be a good homework assignment. The value, the amount of time it takes to go around, there would be an easy homework problem. It would just require you to actually watch a video. The amount of time it would take to go around would be given roughly by this formula, which would be a good check, right? You'd have to, estimate some quantities like how far how long is the axis and how big is the wheel and things like that. But you wouldn't be able to find out the rate at which the wheel was spinning, so maybe not. But in principle, this is something that you could do. And so I would love if I could tell you that this is the end of the story. Unfortunately, it's not. And this is how I ended up getting nerd sniped. Okay, I'm back. Excellent. Just like in the case with the bicycle, we computed the angular momentum relative to the center of mass, not relative to the pivot point, which is supposed to be over here. So we actually didn't account for the fact that there is angular momentum of the center of mass moving relative to the pivot point. And that becomes problematic because in this case, it's not the same direction. Imagine we know that the object is moving forward. The object is moving forward because it's going to rotate this way. And R is pointing to the right. So R cross into the screen points up. So the angular momentum that we would get for this due to the motion of the center of mass points upwards, which is problematic because that's also going to change directions. And so actually what'll happen as this wheel is going around, it'll wobble up and down. It'll wobble up and down as it goes around. That process is called it actually affects the rate at which the precession occurs. So this is not an exact answer because nutation occurs. However, nutation, which is this process of the object bobbing up and down as it goes around, it's a relatively small effect. And assuming that the wheel is spinning sufficiently fast, the wheel's own angular momentum about its center of mass is dominant. So as the wheel spins faster and faster, this effect the nutation effect gets smaller and smaller. But it is a real thing. And so the way I got nerd sniped was that I wanted to go and derive the actual correct answer. And it turns out that there is no So that takes us through to the end of today. There was a little bit more I wanted to talk about, but I kind of got stuck on gyroscopic precession. So we'll just end it there, and we'll continue next time on Monday. I'm going to stop recording here. And I'm going to open the door to questions. God, my Zoom is being